For this next unit, we're going to be looking into exponents and logarithms. The first section that we're going to deal with just deals with exponents, so we'll get to logarithms at a later point. The first problem that we're looking at is we want to graph y equals 2 to the x. Now, this is going to be of the form y equals a times b to the x minus h plus k. So we can see that we've got the vertex form of an exponential model here. But for this particular one, we have no a value because there's nothing sitting out here in front of the 2. We have no h value because nothing is being added or subtracted to the x. And then we have no k value being added to that entire piece. So we've got a fairly simple graph to do here with y equals 2 to the x. So just like anything else, we're going to choose some points that will make sense. Now, with an exponential graph, I would suggest that you choose 5 points, because those 5 points are going to give you a really good idea of what that graph is going to look like. So anytime that we don't have an h value, my suggestion would be -2, -1, 0, 1, and 2. So if we do that, we go -2, -1, 0, 1, and 2 for x. We're going to get 2 to the negative second, so 1 over 2 squared, so 1 over 4. Then 2 to the negative first, 1 over 2. Remember that anything to the 0th power, with the exception of 0, is going to be 1. 2 to the first is 2, and 2 squared is going to be 4. Now, what you'll notice with this is that we got 1/4 and 4, 1/2 and 2. That's going to happen whenever we don't have an h value if you choose -2, -1, 0, 1, and 2. You're going to have this almost symmetrical looking y values. Now, with the exponential form, our starting point is going to be 0, 1. Any transformations of our exponential curve is going to be based off of the starting point of 0, 1. So the a value again is going to stretch, compress, reflect, but it's not going to move it off of 0, 1. The h value will move it left or right from 0, 1, and the k value will move it up or down from 0, 1. So it's not going to be the origin that we're starting with on exponentials, it's going to be 0, 1. When we go and we graph this, we're going to go -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. And so you get a sense that what's going to happen is this is going to get steeper as we start adding more values. So if we were to make this 2 to the 3rd, then when x is 3, y is going to equal 8. If we made this 2 to the 4th, when x is 4, y is going to equal 16. So again, it's going to get steeper and steeper and steeper based off of whatever x value you put in there. Now, there is one more thing that you do need to know here. There is an asymptote here. So we are not going to be able to cross y equals 0. What's going to happen is, as we decrease our x values, as we go further and further into the negatives, what's going to happen is these fractions are going to get smaller and smaller and smaller, but we will never have a value that equals 0. So it's always going to get closer and closer to that asymptote, but it's never going to touch it and it's never going to cross it. All right, so before we move on to problem number 2, there's a little bit of information that we need to go over, and that's regarding exponential growth and exponential decay. Now, think about if you were to put money into the stock market and you look at the line of the stock market, or the Dow Jones, and you see it going from the bottom left to the top right. Then what that's telling you is that the stock market overall is growing, and that's probably going to be good for your stocks. If you ever see the stock market going downwards, or going from the top left to the bottom right, that's probably not going to be a good thing for your stocks. So what we know is that if your stocks are getting more valuable, they're growing in value. So we're going from that bottom left to that top right. Now, we can also have decay, which is going from the top left to the bottom right. Anytime that we look at decay, we might be talking about the scientific principle of a half-life, where the radioactivity of certain elements decreases by half over a certain period of time. Well, that's what we'll often use exponential decay for, and then exponential growth, you'll see we're going to use that for things like stocks or for mortgages, things that go along those lines. Now, in order to figure out whether or not we have growth or decay, we're going to go back to our vertex form here, but we're specifically looking at this value of b. So if b is greater than 1, then we know that we've got exponential growth. We're not going to worry about the a value here. The a value could be negative, the a value could be 1/2, the a value could be 5. It doesn't matter what the a value is. The only thing that we're worried about here is this b value. So again, if the b value is greater than 1, we're going to have a graph that looks like this, exponential growth. If the b value falls between 0 and 1 though, so let's say it's 0.25 or it's 1/8, then anytime that we see that b value falling in between 0 and 1, then we know that we're going to have exponential decay, so our graph is going to look like this. So you want to keep that in mind as you're doing your graphs to see if they match up to what you think you should have when you look at your original formula. For problems 2a, 2b, and 2c, we've been asked to determine if we have exponential growth or exponential decay, and then also to identify the y-intercept of the exponential function. So this is actually fairly easy again. If we're looking at the first one, problem 2a is y equals 12 times 0.95 to the x. So again, what we've got here is y equals a times b to the x. B is going to represent our decay or growth. So if the number is below 1, then we know that it's going to be decay. In this case, 0.95 is below 1, so we know that this problem is decay. Now, the y-intercept is always going to be the a value. Okay? So the a value represents the y-intercept. It's going to be 12 in this case. Over here, we've got 2b, which is y equals 0.25 times 2 to the x. So since the b value is greater than 1, we know that it's going to be growth. The a value is 0.25, or 1/4, so that's going to be our y-intercept. Now over here we've got college savings earns 5% annually, and it's off of a $1,000 initial deposit. Well, we know that if it's a savings account that's earning money, it's going to be growth. You would never put your money into a bank to have the bank take money away from you. So we know that we're going to have growth here, and since the initial deposit is $1,000, that is going to be our y-intercept. In problem 2c, you were given a problem where you were told that you put money into a savings account, an initial deposit of $1,000, and you earn 5% interest every year after that. So one of the things that might be confusing is how exactly is that going to work, or how is that going to fit in to our exponential model? Well, this brings up the concepts of a growth factor and a decay factor. So a growth factor is going to be 1 plus whatever the percentage is for the growth rate. Then a decay factor would be 1 plus the negative growth, which is the decay factor. So in the last one, we had an initial deposit of $1,000, so that would go with A. And then 5%, we can change that into a decimal, that would be 0.05, so that would go in for R. Now, what this is saying is that the amount that you're going to have is a function of the time that the money is in the bank, or it's, if we're talking about half-life, it's the amount that's left over is going to be a function of the time that it's been decaying. So the new amount is a function of the time, and that's going to be equal to the initial deposit, or the initial amount, times 1 plus the rate, and then that is going to be raised by time in terms of years. Now, if we have months, then what we're going to do is we're going to put the number of months over 12. So if we had a 3-month period that we're looking at, it would be 3 over 12, or 1 over 4. So if we wanted to figure out what this problem was here, we would go A of t equals 1,000 times 1 plus 0.05 to the t. Now, go ahead and combine those terms inside of the parentheses, and you would get 1,000 times 1.05 to the t. And you can see how this is now a times b to the x. And so we would have a growth rate that's positive, or that's above 1, so we would have a growth rate rather than a decay rate on that previous problem. Problem number 3 states that you invested $1,000 in 6th grade at a 5% annual interest rate. It wants to know how much is going to be in the account after 6 years. So what we're going to do is we're going to use that formula, A of t equals a times 1 plus r to the t, to figure out exactly how much you would have after those 6 years are up. So what we want to do is identify the information that we need and the information that we don't need. We know that the initial investment was $1,000, so we're going to write that as A equals 1,000. Then it happened in 6th grade. Doesn't matter. We don't care about that part. So we can get rid of that. That's extra information. We do care about this 5% though, because that 5% interest rate tells us what the rate is. So the rate is going to be 0.05. Then how much will be in the account after 6 years? Well, this 6 years represents the time. So we're going to write this t equals 6. So now go back to your formula. A of t equals a times 1 plus r to the t. And all we're going to do is substitute those values in for the variables. So A of t equals 1,000 times 1 plus 0.05 to the 6th. Go ahead and combine these together. 1,000 times 1.05 to the 6th. And again, this 1.05 is going to tell us this is a growth rate. If we were to take a calculator out and figure this out, we're going to get $13.4010. So $1,340.10. So what happened was you made $340.10 in interest on top of your $1,000 initial deposit. So at the end of 6 years, you're going to have $1,340.10 in that account. So for problem number 5, we're given a word problem about the Iberian lynx population. And what we want to do is we want to be able to make an estimate of how many lynx will be living in the wild by the year 2014 if the rate that existed between 2003 and 2004 continues on. So what we're going to do is we're going to again go back to our exponential model, which is y equals a times b to the x. And we're going to change that over to a times 1 plus r to the t. So all we need to do is find the rate, and then that becomes our b value. So we need to go back to our change of rate formula, our percentage change formula, which is new versus minus old over old. So we're going to take the population that existed in 2004, which we're going to consider the new population, and that's going to be 120 minus the old population, which was 2003, so minus 150 over the old population of 150. So we end up getting negative 30 over 150, which reduces to negative 1/5 or negative 0.2. So we can now take this, the rate, and put it into this formula here. So we get a times 1 minus 0.2 to the t, or a times 0.8 to the t. Now what we need to do is go back and look at the initial amount. The initial amount was the year 2003 when there were 150. So we've got 150 lynx in the population in 2003, and the decay rate is going to be 0.8, and then the number of years that we've got here, going from 2003 to 2014, that's going to represent t. So there's going to be 11 years there. So we're going to plug in 11 for t, and that's going to give us the amount after 11 years. So a of 11 is equal to this. Well, that's going to be approximately 13 lynx. So after 11 years, based on the exponential model, there would only be 13 of the Iberian lynx left in the world, if the current or if the population trends from 2003 to 2004 held true.